December 12th, 1978, 3:10 a.m., the North Atlantic.
The MS München, a 261-meter German cargo ship built to survive anything the ocean could throw at it, sends fragmented distress signals. The messages are brief, confused, desperate. By 7:34 a.m., they stop. All 28 crew members are gone. When searchers comb 200,000 square kilometers of ocean, they find debris, empty life rafts, oil-smeared buoys, life vests, and one piece of evidence that makes no sense whatsoever.
A lifeboat, torn from its moorings 20 meters above the waterline, 66 feet up the side of the ship, secured with steel pins designed to hold through any storm. The forward-mounting pins were bent backward, as if something had struck the ship head-on, with enough force to rip a multi-ton lifeboat from reinforced brackets positioned higher than a 6-story building.
The official investigation concluded only that severe weather caused an unusual event. They couldn't say more, because according to every wave model, every statistical analysis, every piece of accepted oceanographic science, the wave that killed the München wasn't supposed to exist.
This is the story of how scientists discovered that the ocean has been hiding something from us. Something that appears without warning, defies our understanding of physics, and has been sinking ships for centuries while we dismiss the survivors as liars and fools.
The München wasn't the first.
For centuries, sailors returned from voyages with stories that made them sound insane. Walls of water appearing from nowhere in otherwise manageable seas. Waves towering over their ships like moving mountains. Ships vanishing without distress. Calls in weather that shouldn't have been fatal. And always the same detail. The wave came from nowhere, impossibly tall, impossibly steep, impossibly sudden.
In 1826, French explorer Jules Dumont d'Urville reported encountering waves 33 meters high in the Indian Ocean. His colleague, physicist François Arago, publicly ridiculed him. Anything taller than 9 meters violated the known laws of wave mechanics. D'Urville's reputation suffered, and other sailors learned to keep quiet. Even Ernest Shackleton's 1912 account, "For God's sake, hold on! It's got us!" was filed away as an anomaly. The pattern continued, ships lost in calm seas, damage suggesting impossible impacts, survivors describing the unbelievable, and scientists again and again explaining why these accounts couldn't be trusted. Waves followed statistical distributions. A wave twice the height of its neighbors should occur only once every few thousand years. 3 times the height, once every 100,000 years. The math was clear. The sailors were wrong. Even the München's bent lifeboat pins, physical evidence that something impossible had struck the ship, weren't enough to change scientific consensus. Without measurements, without data captured in real time, the wave itself remained theoretical, a mystery without proof.
That changed soon. January 1st, 1995. The Draupner oil platform, North Sea.
An automated laser sensor records something that shouldn't be possible. A wave over 25 meters high passes beneath the platform. The surrounding seas average 12 meters. This isn't a gradual swell or a storm surge building over time. It's a single wave, more than twice the height of everything around it, appearing and disappearing in seconds. The data is checked, rechecked, analyzed by multiple teams. There's no equipment malfunction, no measurement error. The wave was real. For the first time in history, science had proof. Rogue waves existed. The floodgates opened. Researchers began examining satellite data, ocean buoy records, ship logs that had been dismissed as unreliable. What they found was staggering. Between 2011 and 2018 alone, 210 confirmed rogue wave events were documented. They weren't once-in-a-millennium anomalies. They were happening constantly, all over the world's oceans, and we'd simply refused to believe they were real. In 2020, sensors off British Columbia near Ucluelet captured the most extreme rogue wave ever recorded. 17.6 meters tall in seas where surrounding waves averaged just 6 meters. It was almost 3 times taller than everything around it, a statistical impossibility that the ocean produced anyway, as if mocking our equations. But documenting rogue waves was only the beginning. The real mystery was deeper. What mechanism could create a wave that violated every model we'd built?
Scientists aboard the icebreaker S.A. Agulhas, too, spent months in the Southern Ocean using 3D imaging to track wave formation in real time. What they discovered in 2024 rewrote our understanding of how oceans behave. Rogue waves don't form randomly. They require a narrow window, young seas where waves are still responsive to wind, strong winds creating steep wave fields and chaotic conditions. Under these precise circumstances, one wave begins stealing energy from its neighbors in a runaway process called self-amplification. The wave doubles or triples in height while everything around it shrinks. Then, as quickly as it appeared, it collapses.
Certain locations amplify the risk dramatically. Off South Africa's southeast coast, the Agulhas current flows southward at up to 5 knots, directly opposing westerly winds from the Southern Ocean. When storm waves meet this current, they steepen and compress, creating conditions where rogue waves appear with terrifying regularity. Over 150 ships have been lost there in recent decades, many vanishing without explanation in seas that seemed survivable.
The München likely encountered a rogue wave in exactly these conditions. The wave struck the bow, smashing the bridge and superstructure, causing immediate power loss and a 50-degree list. The ship drifted for roughly 33 hours before sinking. The wreck has never been found.
But rogue waves represent only one piece of a larger mystery. Because while scientists were finally accepting that the ocean could produce waves that violated our models, geologists were discovering something even more disturbing. The ocean wasn't the only thing producing impossible waves. On the island of Tongatapu in the South Pacific, there's a boulder the size of a small house sitting 128 feet above sea level, more than 200 meters inland from the nearest cliff. It weighs over 1,200 tons. For decades, no one questioned how it got there. Mountains shed rocks, boulders rolled downhill. Simple. Then researchers from the University of Queensland examined it closely. The boulder wasn't from a mountain, it was coastal limestone, identical to the cliffs below. And it hadn't rolled, it had been lifted, carried uphill, deposited 128 feet above the ocean by something with enough force to move over 1,200 tons of solid rock like driftwood.
Using uranium-thorium dating, they determined the boulder was placed there approximately 7,000 years ago. Computer modeling suggested only one explanation. A mega tsunami with waves exceeding 50 meters had struck the island, likely triggered by a submarine landslide following an earthquake.
The boulder wasn't alone. Across the Pacific, researchers began finding similar evidence: massive stones in impossible locations, ancient destruction layers in coastal sediments, geological scars that told stories of waves far larger than anything in recorded history. In Scotland, sediment cores revealed tsunami deposits reaching 29 kilometers inland, dated to approximately 8,200 years ago. The source, the Storegga Slide, a submarine landslide off Norway's coast involving 3,500 cubic kilometers of seafloor, an area larger than Iceland that collapsed and slid into the North Atlantic. The resulting tsunami sent waves exceeding 20 meters across 600 kilometers of coastline. Researchers estimate it may have killed up to 25% of Britain's Mesolithic population in a single day.
But even Storegga pales beside what happened in Alaska on July 9, 1958.
10:16 p.m. Lituya Bay, Alaska. Howard Ulrich and his 7-year-old son were asleep on their fishing boat, the Edry, anchored in a narrow fjord surrounded by mountains. The shaking woke them, a magnitude 7.8 earthquake on the Fairweather Fault. Ulrich had felt earthquakes before. This was Alaska. But then he heard something that made his blood freeze, a sound like an explosion at the head of the bay. He looked up and saw the mountain collapsing. 30 to 40 million cubic meters of rock, 90 million tons, shaking loose from 900 meters above the water and falling in seconds. The rockfall hit the water with such force that it created a wave unlike anything in recorded history.
Ulrich's anchor was stuck. He put a life preserver on his son. He prayed. Then he released the anchor chain and steered directly into the wave. The wave face was smooth, almost glassy, rising over 75 feet high. It lifted the Edry like a toy, carrying them near Cenotaph Island, snapping the anchor chain, depositing them in the center of the bay amid 20-foot chop, ice chunks and floating logs. They escaped around 11 p.m., their boat battered but intact. Bill and Vivian Swanson, anchored near the bay entrance, saw the wave approaching and rode it bow first, lifted high above the tree line before being set back down. They survived. The third boat, the Sunmore, was anchored closer to the rockfall. It vanished completely. The two crew members were never found. When geologists surveyed the bay days later, they found something that seemed impossible: a trim line, the boundary between forest and bare rock, extending over 500 meters up the opposite slope. The wave crest itself had reached about 150 meters, but the force of the water had carried trees, soil and vegetation up to 524 meters, taller than the Empire State Building. The trim line is still visible from space. Computer modeling later revealed why Lituya Bay produced such an extreme wave. The narrow geometry of the fjord acted like a funnel, concentrating the wave's energy instead of allowing it to dissipate. If the same rockfall had occurred in open ocean, the wave would have been a fraction of the height. Location was everything. As researchers pieced together the evidence, rogue waves, megatsunamis, submarine landslides, a pattern emerged. These weren't separate phenomena. They were all expressions of the same underlying truth. Earth operates at extremes we're only beginning to understand, and the conditions required for these extremes are far more specific and far more common than anyone imagined. But the ocean was hiding something else, something beneath the surface. In 1893, Norwegian explorer Fridtjof Nansen's ship mysteriously slowed to a crawl, despite full sail and favorable winds, held back by what he called some mysterious force. He couldn't see what was happening. His ship was creating internal waves at the boundary between Arctic meltwater and the denser ocean below. It wasn't until 1904 that Swedish oceanographer Vagn Walfrid Ekman identified the mechanism through laboratory experiments. He called it dead water. Modern research using submersibles and sonar has revealed internal waves in the open ocean reaching 200 meters tall, taller than most tsunamis, moving through the depths completely undetected by anyone on the surface. These hidden giants transport enormous amounts of energy and nutrients through the ocean, affecting everything from fish populations to climate patterns. Yet we've barely begun mapping where they occur and how they behave. Here's what keeps oceanographers awake at night. We've explored less than 5% of the ocean floor in high resolution. The waves that pose the greatest threat to coastal populations, compound earthquake landslide tsunamis, submarine landslides like Storegga, rogue waves in major shipping lanes, are the ones we understand least. In 2024, the Noto Peninsula earthquake in Japan triggered multiple submarine landslides roughly 50 seconds after peak shaking. The landslides amplified tsunami heights just enough to overwhelm coastal defenses designed for earthquake-only tsunamis. The wave arrived in two distinct surges, one from the earthquake, one from the landslides. Warning systems predicted the first surge. They missed the second. Somewhere right now, sediment is accumulating on an underwater slope. A fault line is building stress. A storm is generating young, chaotic seas in the Southern Ocean. And when the conditions align, when geology, oceanography, and physics converge in exactly the right way, Earth will produce another wave that rewrites our understanding of what's possible. Off the coast of Hawaii, the Helena Slump,
A massive section of the Big Island's southern flank is slowly sliding toward the ocean. It's estimated at 5,000 to 12,000 cubic kilometers of rock, making it hundreds of thousands of times larger than the landslide that created the Lituya Bay wave. Geological evidence from similar Hawaiian landslides suggests catastrophic collapses have happened before. Roughly 120,000 years ago, a massive failure on Mauna Loa deposited coral debris 300 meters above sea level on the island of Lanai. The Helena slump is currently moving at about 10 centimeters per year, though this motion can stall for long periods. Scientists debate whether the next movement will be gradual or sudden. Recent research has identified a large undersea ridge that may act as a buttress, potentially preventing a complete collapse. But if that buttress fails, if the entire mass destabilizes in minutes rather than decades, computer models suggest waves exceeding 300 meters could strike the Hawaiian Islands within minutes, with 30-meter waves reaching the US West Coast, Japan, and Australia within hours. This isn't science fiction, it's geology, and we have no way to predict when it might happen. The Tonga boulder sat on that hillside for 7,000 years before anyone understood what it meant. The München's lifeboat was recovered in 1979, its bent mounting pins telling a story no one wanted to believe. Sailors reported rogue waves for centuries before a single laser sensor finally proved they were telling the truth. The technology exists to monitor these threats. Researchers at the University of Maryland have developed AI systems that can forecast 73 to 75% of rogue waves before they form. What's missing is the funding and the will to deploy them systematically. We treat ocean research as a luxury rather than a necessity, even though more than 40% of the global population lives within 100 kilometers of a coast.
The ocean has been hiding something from us, not because it's malicious, but because we refused to look. We built models that told us what was possible, and when reality contradicted those models, we dismissed reality.
The waves that shouldn't exist are real. They're happening right now, all over the world's oceans. And the only mystery left is whether we'll understand them before the next one strikes.
If you think we should be exploring more of our own planet before we explore others, subscribe to witness more of Earth's unsolved mysteries that are hiding in plain sight.